Our next paper will continue our look at Fischer-Tropsch catalyst, and Ram Srinivasan from University of Kentucky Center for Applied Energy Research will present an electron microscopy study of that.
What is the title slide? Oops.
You should have shown it.
Well, thank you. The talk now I'm going to give will be on the Fischer-Tropsch iron oxide catalyst used for the Fischer-Tropsch synthesis. We have done some electron microscopy work on this iron oxide catalyst. In our ongoing research on this Fischer-Tropsch synthesis, the contract we obtained from the DOE, we have been looking at various catalysts such as promoted iron oxide catalyst, co-precipitated catalyst, then the co-precipitated, then promoted by potassium. All kinds of catalysts we have been looking at this for Fischer-Tropsch synthesis. Now, as you know, the Fischer-Tropsch synthesis involved the conversion of carbon monoxide and hydrogen mixture over a catalyst bed to the hydrocarbons. Again, the process involves lots of variables. Then the process is operated at very high pressures, and again, there are lots of controversies that are still today existing, what are the species that are responsible for the catalytic activity and selectivity for this Fischer-Tropsch synthesis. Where some people say the carbide is formed during the Fischer-Tropsch synthesis, and the carbide phase is responsible for the selectivity and activity. And some people say that as soon after the carbide is formed, it's converted to magnetite. That's Fe3O4, and some people argue that that is the phase that's responsible for the activity, and so on and so forth. So, as far as the activity and selectivity of this Fischer-Tropsch catalyst are concerned, there are still controversial arguments as to which one is directly responsible for the activity or selectivity. So, now I will be giving short introduction. I think I've already given the introduction. So I'll go through some experimental conditions, what the conditions we followed for our catalyst, and then which will be followed by results and discussions, and then I'll follow with some conclusions. Oops, I already changed this. Okay. In addition to various catalysts we studied, the one that I'm going to submit some of the data are on ultra-fine catalysts that we obtained commercially. These slides gives you the specifications of the ultra-fine catalysts we obtained from Mark 1, Massachusetts, Mark Incorporated, Massachusetts. This is the history of the starting iron oxide powder. The typical properties of this starting material, iron oxide catalyst, is this is in alpha form given by the vendor. The physical form is very free-flowing powder and with a very low density. Bulk density is less than 0.05 gram per cc. When you open the box, the powder will just fly in the air with very less bulk. However, it should be noted that the surface area of this is very high. So I want to emphasize this point. We are now starting with a very high surface area iron oxide catalyst. Again, this is not promoted iron oxide catalyst, just an ultra-fine iron oxide catalyst to start with high surface area. So we took this catalyst and then pre-treated in the system. Okay, this is the electron micrograph from the, can you focus it? It's not in focus. This is the electron micrograph obtained from the as received iron oxide powders. As you can see here, they are all extremely fine particles in the range of about 20 to 30 angstroms in size, with a very high surface area of about 250 to 300 angstroms. 300 meters square per gram. So this is the electron micro diffraction pattern obtained from 5 nanometer region from one of these small particles, showing very diffuse rings that these particles are all maybe amorphous state to start with. It's not working. This is a high resolution electron microscopy. As you can see here, these are the lattice fringes for gamma Fe2O3, showing that these are 440 fringes and 311 fringes. This is again from the as received Fe2O3 catalyst. Now, this was subjected to the Fischer-Tropsch synthesis reaction. Now, for this, we took about 2 grams of iron oxide catalyst and then put it in the continuous stir tank reactor. Then we pre-treated this catalyst by passing carbon monoxide for about 24 hours at 100 psi and at about 260 degrees Celsius. And then this pre-treatment appears to give better activity than without the pre-treatment. So that's the reason the pre-treatment was given with carbon monoxide at this temperature for about 24 hours. Then after this catalyst has been pre-treated in carbon monoxide for about 24 hours, then the reaction mixture was introduced into the reactor. The carbon monoxide hydrogen ratio of 1 was introduced, and then the catalyst samples were withdrawn at regular intervals from 2 hours to about 72 hours. So this 2 hours to 24 hours time periods are the catalysts that are there in the actual stream and in the Fischer-Tropsch stream conditions. So these catalysts that were withdrawn after these time intervals were analyzed in the electron microscope to check the particle morphology and various crystalline phases, what kind of carbide phase is formed, whether it is magnetite is formed, how the particle shape morphology looks like for all these catalysts. So for this we have used a Hitachi H800 nanoprobe microscope. This microscope is equipped with a very, very fine thin electron beam. We can control the electron beam as low as 2 nanometers. That means we can focus the beam to as small as 20 angstrom region and then can take the crystallographic information from that. That is why it's called a nanoprobe mode. The nanoprobe modes that are available are 2 nanometers, 5 nanometers, and 10 nanometers. That's 100 angstroms. So using these 3 thin probes, electron probes, we can obtain precise crystallographic orientation from these extremely small particles, 5 angstrom, 50 angstrom, 100 angstrom particles. Okay, this is the electron micrograph obtained from the iron oxide catalyst, which was pre-treated for 24 hours and then which was in the synthesis gas stream for 2 hours. And then, as you can see here, the particle size has not grown too much. Again, the particle size still is intact. The particle size distribution is about 40 to 50 angstroms. Absolutely, there is not significant growth in the particle size. This insert is shown here from one of the electron micro diffraction pattern obtained using a 2 nanometer electron probe from one of these particles, individual particles, which show that this particle is a Fe3C, that the carbide phase is formed, which is oriented in 1,1,0 direction. Again, these small particles are all, very together. They are all very agglomerated. So getting an individual particle is a strenuous task. So if you hit the electron beam, 5 nanometer electron beam, then it should hit exactly an individual particle in order to get a nice pattern that can be solved. Otherwise, you get diffraction patterns from 3-4 different particles if they are together. That will be a messy pattern, it will be difficult to solve the pattern. So we have to group for small individual particles in order to get the diffraction patterns. This is again particle size distribution obtained from the 2-hour sample. Again, we take about 20, 30, 40 micrographs from different regions of this catalyst, and then count more than 1,000 particles in order to get a nice distribution, particle size distribution for this catalyst. As you can see here, after 2 hours in the stream, the particle size is again the major fraction of the catalyst lies in the range of about 30 to 50 or 60 angstroms. So there is not much, there is not significant growth in the particle size after 2 hours in the stream. Now after 10 hours, what happens? This is the catalyst that has been there in the stream for 10 hours. Again, you can see there is a slight growth of the particle size. Then if you look at the particle size distribution for this catalyst, again, there's a growth from about 50 angstroms to about 120 or 140 angstroms. So the major fraction after 10 hours lies in this range of about 100 to 160 angstroms inside. There's a slight growth after 10 hours. Again, the micro diffraction patterns obtained from these particles show the carbide phases such as Fe3C, etc. Now this is the electron micro diffraction pattern obtained from one of those dark particles, and if you solve it, this mostly for 2 hours or 10-hour samples, mostly we see Fe3C phase from all these particles as calculated by the diffraction patterns. And in addition to this, we have seen some of these particles are light, whereas some of the particles are very dense and dark particles. The dark particles, the diffraction patterns obtained from these dense, dark, small particles consistently showed the Fe3C patterns, whereas the light particles showed consistently the iron oxide phase, Fe3O4. Therefore, this is the diffraction pattern from one of those small light particles, or less transparent particles, which shows the Fe3O4. So even after 10 hours in the stream, we are able to see both phases, magnetite phase as well as Fe3C carbide phase. Fe3C cementite phase. Now, in addition to the Fe3 phase, the Fe3C phase, we also have seen some particles to give Fe7C3 particle orientation in 110. So mostly after 10 hours in stream, we were able to see mostly Fe3 phase, cementite phase, but however some of the particles showed Fe7C3 phase, and the transparent light particles showed Fe3O4, showing that there has been a conversion or the transformation going on. And when you go to 24-hour sample, okay, this is the EDX, this is the energy dispersive X-ray analysis. The instrument is also equipped with an Edx detector, the lithium single crystal Edx detector. By focusing this 5 nanometer electron probe on the sample gives off the X-rays, and thereby we can pick up, using the X-ray detector, we can pick up the intensity of the elements that are coming out from the sample. And this is a typical EDX pattern using a 5 nanometer probe from a small 5 nanometer particle, showing again the Fe K alpha and Fe K beta lines for that particular particle. This copper K alpha, copper K beta lines are from the grid, since we are putting the samples on the copper grid. So this is coming from the grid, not from the sample. So for all these particles, whether they are dense, dark particles, or they are the thin, transparent particles, the EDX patterns showed only the iron K alpha lines. because we cannot pick up the carbon line, C line, or oxygen line because of the limitations of our detector. The detector cannot pick up elements below number 11, atomic number 11. So here is the treated catalyst for 24 hours in the stream. And again, you can see here the particle size grows gradually here from 10 hours to 24 hours. And also you can see here, in addition to all these dark particles, you can see some of these, light particles, which have been converted to, say, Fe3O4 phase. If you look at the particle size distribution, you can clearly see the light particles and the dark particles were counted, lots of them were counted, and then but the size between there's not a significant difference in size between these light particles and dark particles. So these light particles, that is transparent light particles, were identified as the magnetite phase, the Fe3O4 phase, and these dark particles were identified as carbide phase. And then this slide shows that there is not much difference or in size between these carbide particles and magnetite particles. This is the electron micrograph obtained from the sample after it has been in the stream for about 48 hours. Again, you can clearly see here the particle size growth. The light particles, these are the light particles, very transparent particles, and these are the very dense dark particles. And the electron micro-diffraction patterns could be obtained from these particles individually, separately, and also from these light particles. So these were found to be magnetite, and these dark particles were found to be carbide phase. Then after, this is the particle size distribution obtained from the 48-hour sample. Again, the major fraction lies about in the 160 to 200 to 240 angstrom in diameter. Now, this is the pre-treated sample. This is the iron oxide treated for 24 hours, and after it has been in the stream for about 72 hours. Again, the particle size has grown a little bit larger. And this is the again in this sample you can see lots of light transparent particles, more than the dark particles. And if you look at the particle size distribution for this sample, again the particle has grown to about 300 angstroms in diameter. So there was a hypothesis from Thompson's group in Washington State University that they say that particle size has an effect in the activities, catalytic activity, and selectivity of these Fischer-Tropsch catalysts. Also, this is the summary of all the particle size distributions we have got for 2-hour samples to up to 72-hour samples. As you can see here, the particle after 2 hours, the particle size, the major fraction lies in the 3 to 5 or 6 nanometer range, and then it grows to about 300 angstroms after about 72 hours in the stream. So there's a slight particle growth here. Then from after 2 hours, it grows to about 140 angstroms. Then after 10 hours up to about 48 hours, there is a small growth. And then after 48 to 72 hours, there's a little bit growth up to 300 angstroms or so. So now if we plot the peak, major peak in those particle size distribution with the synthesis time, you can see there is a rapid growth initially up from 0 to 10 hours, and then there is a small, very small growth of particle size in this region, and after 72 hours it just goes there. But if you ignore the 72 hours, it's just the particle size is somewhat getting a constant value over there. Now, again, another particle morphology was seen for the 72-hour sample. There is again a core shell type morphology. This could tell us something about what transformation of the conversion is going on. Again, some of this carbon monoxide hydrogen mixture can diffuse through the carbon, layer on top of the particles and diffuse through and then convert the magnetite into carbide. This was the suggestion given by the Thomson Group, Washington State University. So this core and shell type morphology was seen for the 72-hour sample, and if we take the diffraction pattern, the electron micro diffraction pattern from this core, it shows the iron carbide phase, as you have seen here, this Fe3C111 orientation. This is the experimentally obtained diffraction pattern, and this is the theoretically generated diffraction pattern, and you overlay this pattern on the experimental to solve the diffraction patterns. So the diffraction patterns obtained from the core shows that they are all Fe3C fit, whereas the shell type we are not able to get any diffraction pattern from the shell because of the thickness. The shell thickness is too small for us for the beam to look at and get any diffraction patterns. So looks like we have to go to high resolution electron microscopy. If you go to high resolution electron microscopy, we can see the shell, what type of shell, what type of phase or what kind of phase it is there on the shell type. So the core has been identified as the carbide phase. So if we now plot the light particle, the transparent particles and the dark particles for the 24-hour sample, the number of particles, the number of transparent particles are less, and the number of dark particles are more here. This is about 10,000 to 11,000 particles were counted, as you can see here. So after about, say, 24 hours in the stream, the catalyst mostly consists of a major fraction of carbide phase and a minor fraction of the oxide magnetite phase, Fe3O4. And after 72 hours, all this, the conversion takes place, or the transformation of carbide to oxide takes place, and you have major fraction of the catalyst is Fe3O4 magnetite phase, and the Fe3, the carbide phase is also equally present after 72 hours, and again. So if we calculate this percentage Fe3O4, okay, that's that. If we plot the percentage Fe3O4 that is formed in the catalyst with reaction time or synthesis time, our study showed that it's starting from about 20% Fe3O4 in the stream to about 60% after 60 or 70 hours, 72 hours in the stream. Huang et al., my earlier colleague, he did this, the same catalyst, he used the same catalyst and then did this Fischer-Tropsch synthesis, and using mass bar spectroscopy, he calculated that the percentage of Fe3O4 follows this line, going from about 30% to about 100% Fe3O4 after 100 hours in the stream. This is just a comparison of this. So this, coming to the conclusions of the study, that we have seen mostly carbide phase is formed in the initial conditions of the Fischer-Tropsch synthesis, and as the time goes on, the conversion or transformation takes place from iron carbide to iron oxide. This could be either due to the carbon monoxide or due to the water that is formed within the reaction during the synthesis of this Fischer-Tropsch synthesis. And I would like to acknowledge the chemical engineer who carried out all this reaction studies, Li Guangzhou and Shivraj, who did some micro diffraction patterns, solving the programs, etc. And also the contract awarded by the US DOE is acknowledged, the Commonwealth of Kentucky is acknowledged. Thank you. I'll be having a chance for questions.
Questions? Yes. Please step to the mic, please.
Hi, Eric Lowell from University of Delaware. Have you made any effort to try to correlate the activity or the selectivity of the catalysts with the relative fractions of the carbide or nanotech phases?
Okay, from this study, we have taken only 2 grams of the catalyst and then took hardly a few milligrams or hardly 0.1 or 2 grams at each regular time interval. So we were not getting any activity or selectivity. We were not measuring any products for this particular study because we were interested in following the morphology of these particles and the crystalline structures. So we did not do any activity selectivity for this. Yeah.
Cal Bartholomew, BYU. Could you tell us something about the limits on your ability to measure very small particles, let's say less than 20 angstroms of either metal carbides or iron particles, metallic iron particles that might be present in this catalyst and could account for the activity, since, as you point out, this is still a controversy.
Right, there's still a controversy. Some people think that this, to start with, it is in the iron oxide form. Some people think that it is reduced to metallic iron, very small metallic iron, and then it goes to carbide. And then, so some people still argue that this metallic ion, small particles of metallic ion could be responsible for the selectivity and activity. As for your question, the limitation of this nanoprobe is just 2 nanometer. That's the limitation of an electron probe. So if you have, say, 20 angstrom particles, again, these 20 angstrom particles have very, very less number of diffracting planes. Very tough to get diffraction patterns from these 20 angstrom particles because they don't have a very, very minimum number of diffraction planes. If you have a very, very minimum number of planes, about, say, 20 angstrom particles may have hardly 3 or 4 planes. So in that case, you cannot get the diffraction patterns. You will get the transmitted beam, that's all. You will see only one middle spot, the transmitted beam, that's all you can get.
So you really can't rule out the possibility then?
Yes, you cannot rule out the possibility.
Small carbide or iron metal particles.
Right.
Yes.
John from University of Pittsburgh, previously from Washington State. And I have one question about the iron carbide phase you obtained from electron diffraction. Isn't your reaction temperature too low to have cementite? In most literature studies, instead of Fe3C, usually you see Fe 2.5 right, or 2.2 in the temperature range.
Right. The literature, yeah, I have seen some of the literature, they say that high carbide is formed, that's Fe 2.2C. So you have lots of carbides in this FEC system. In FEC system, you have TP carbides, O carbides, where carbon atoms are located in orthogonal interstitials, and TP in the trigonal prismatic interstitials, etc. So some of the people have reported that, especially Thompson's group from Washington State University, using in-situ X-ray diffraction, they have reported this. They have seen chi carbide, that is Fe 2.5, 2.2, 2.5C. As far as our electron micrograph, these are the operating conditions. Here we are operating at 100 psi, very 100 psi pressure, and also 260 degrees Celsius. So we have seen only this Fe3C or Fe7C3 phase, but I have not seen the Fe 2.5C in this catalyst.
Second question is, the amount of magnetite in that catalyst system is all depending on how much conversion you have. If you have large conversion, you have more water or CO2 in the system, which then oxidize those carbides. So without that conversion data, having those iron oxide composition change is kind of vague.
Well, activity, Bert, did you do it?
The study which Huang did, we did measure conversion. The conversion of this catalyst is 60–70%. We have run this catalyst for up to 6 months in a continuous stirred tank reactor, unpromoted, with essentially no loss in activity. Professor Emmett in 1974 made the comment that if you start out with a carbide catalyst, with use it gradually changes to the oxide. Activity doesn't change, selectivity doesn't change. With this catalyst, we start with the carbide when we use CO pretreatment. If we use hydrogen, we do get metallic. Within 2 hours, it forms the carbide. If we start out with hydrogen CO, it's partially converted to carbide. So we have measured activity with this. At high water, it does go to the oxide and comes to essentially a steady state.
Other questions? Bob?
Bob Gormley, Department of Energy. I'd like to echo the same comment as the last speaker. I think I would expect to see the Chi carbide, and I'm surprised you don't, and to go along with that, like the Mossbauer work of Jerry Hoffman in Kentucky, starting out in CO pretreatment followed by syngas. You see Chi carbide and some epsilon carbide, and at the Department of Energy, we did the same, starting up as you did, again with taking samples out and using Mossbauer. It is a bulk technique. Again, I suggest Chi carbide.
Well, I've not seen any Chi carbide.
With this catalyst, no. With other catalysts, yes. But not with this catalyst.
Because we are starting with, this is the catalyst that we start with the high surface area, commercially obtained catalyst, this ultra fine iron oxide catalyst.
And the Mossbauer data was by Huffman.
Other questions? Okay, thank you, Ron. Our next paper is